Hi, everyone. Thank you all for coming to our talk today. Our talk is called Scaling Smarter, Not Harder, How Extending Cluster Autoscaler Saves Millions. My name is Ben, and I'm here with my colleague Rahul, and we are both software engineers at Datadog. So we're going to start today by talking a little bit about how we do node autoscaling at Datadog, before diving into the cluster autoscaler and the concept of expanders. And then we're going to move into talking about how we identify optimal instance types, and then how we scale those optimal instance types. So first, a bit about Datadog. We run Kubernetes from scratch in a multi-cloud environment. We run across dozens of clusters with tens of thousands of nodes and hundreds of thousands of pods. And within this infrastructure, we serve trillions of data points per hour for over 30,000 customers. At Datadog, Rahul and I both work on a team called Compute Autoscaling. At a high level, the goal of our team is to manage the node infrastructure for product teams, to enable product teams to focus on product development while we focus on the node infrastructure. In doing so, we focus on things like scheduling and scaling efficiency to deliver nodes as fast as possible, as well as bin packing and cost optimizations across our fleet. So a key offering of our platform is something that we call a node group set. So first, a node group we can think of as a cloud provider agnostic representation for something like an autoscaling group or a managed instance group. If you're familiar with the cluster autoscaler, you might be familiar with their concept of a node group, and ours is similar, but we have a custom resource definition defined in our environment that we use for node groups. We have one more abstraction on top of a node group, which we call a node group set. A node group set is a set of node groups that falls under the same scheduling domain. So what that means, if an application specifies a toleration or a node affinity for our node group set, then they could schedule onto any of the underlying node groups that would fit their pod. So node group sets are beneficial for us for a few reasons. One of them is it makes it a lot easier for us to onboard and manage many users and many applications across Datadog, because they can just set the specification for the node group set, and then we can change out the underlying node groups or instance types beneath them without them changing anything else on their application. Additionally, node group sets are an easy way for us to provide multiple instance type options. So for example, we want to serve a diverse set of pods with lots of different resource requests, so we can provide large nodes to serve those or smaller nodes. As well, if we were to run out of capacity for any one instance type, we want to be able to quickly fall back to another instance type, and node group sets give us an easy way to do that. So for node autoscaling at Datadog, we use the cluster autoscaler. And for the sake of time, I won't get into too much detail about why we use the cluster autoscaler over other autoscaling alternatives. But at a high level, one of the main reasons we use cluster autoscaler is because it has support for all the cloud providers that we need within our infrastructure. As well, we've been running cluster autoscaler for a while now, and we're happy with the operational experience we've been having in our clusters, and have been able to contribute upstream with features when we need them. So to dive into how instance type selection works within the cluster autoscaler, we can say, let's say we have a pending pod that needs to scale up. The autoscaler will first start with all of the node group options, and then it will filter down to the node groups that are able to schedule this pod via scheduling simulations. And then if there are still multiple node groups that can schedule the pod, it will use the concept of expanders to pick the best node group to scale. So we can think of an expander as a strategy to pick the best node group in order to trigger a scale-up to schedule the pod. Within the cluster autoscaler, there are a few built-in expanders. The most simple one is random, which will just select a random node group. Another option is the least waste expander, which will select the node group that will waste the fewest amount of resources when fitting those pods. Another is price, which selects the cheapest node group option. Another one is priority, where users can assign specific priorities to node groups, and the cluster autoscaler will respect those priorities. You can also stack expanders, meaning that you can specify one and then another. For example, if I specify the least waste expander and there's still a tie, it would fall back to the random expander and pick randomly to ensure there's always one choice. So for us, as a reminder, one of our goals is to optimize for bin packing efficiency and reduce waste. So we thought the least waste expander would be a good choice for us. So to dive into a bit of a case study, we can see we have a node group set here that's very simple, offering one 16-core machine and one 8-core machine. And if a pod comes along requesting 6 cores, the least waste expander will tell us that we should scale up the 8-core machine, and this pod will schedule. Now, if another pod comes along requesting 9 cores, well, now that can't fit on the 8-core machine, so we need to scale up a 16-core machine. And we can quickly see that in this case, we now have 9 wasted cores. So in our optimal scenario, we would have bin packed both of these pods onto a single 16-core machine, and now only have 1 wasted core. So there are a few ways that we could get to this. You might notice that if the 9-core pod came first, we would have scaled up a 16-core machine, and then the 6-core pod could have fit on it. Similarly, we could rely on repacking with the cluster autoscaler in order to pack these pods together after the fact. However, this example still gave us motivation to take a look at our fleet in practice to figure out if this theoretical bin packing optimization was possible. So we took a look at all of our node group sets and all of our clusters, and specifically at our requested CPU percent for these node group sets. And we realized that while we're pretty good about bin packing in many of our node group sets, there's clear opportunity for improvement in many clusters and many node group sets. And our clusters are lots of different sizes, so to be more concrete, we translated this CPU request percentage into the actual dollar impact, and we realized that if we were to improve our bin packing, there's some significant cost impact that we could bring. However, we also know that instance type selection goes beyond just bin packing. We also care about things like the performance of each instance type. We care about whether the cloud provider has enough capacity to serve our entire fleet. And we also know that within specific clusters, we might have specific instance type preferences to meet the application needs that run in those clusters. And as a reminder, we run across multiple cloud providers in dozens of clusters, so we have to make this decision in more than just a single cluster. And as I mentioned, each of these clusters might be unique in the applications that they run. For example, one might serve more network-intensive applications and therefore benefit from network-intensive instance types, et cetera. So at this point, it might seem like there's no one expander fits all solution that we can use across our entire fleet. However, the cluster autoscaler provides something called the gRPC expander. So the gRPC expander allows users to build a gRPC service to make custom node group decisions. So when it comes time for the cluster autoscaler to pick the best option, it will make a request to the gRPC expander, and within that service, you can return what you have determined is the best option to scale up. Here's an upstream example that the cluster autoscaler provides for the gRPC expander. In this example, the strategy is simply to choose the option that has the longest node group ID name, but you could replace this with whatever arbitrary logic would fit your needs. So at this point, we've recognized that we have an opportunity to improve our fleet's efficiency via better instance type selection, and the gRPC expander gives us the ultimate flexibility to make these instance type choices. So our goals became simple. We wanted to identify the best instance types, and we wanted to scale the best instance types. So to simplify the criteria that we'll use for instance type selection, we'll bucket it into 3 high-level ideas that we care about in instance type selection. We care about the cost of our fleet, we care about the performance of the applications that run on them, and we care about the reliability of our fleet. So beginning with cost, I want to return back to the bin packing problem that I showed earlier. But in reality, this problem is a lot more complicated than just 2 pods requesting CPU. We actually serve lots of different pods, having lots of different CPU or memory requests. And as a reminder, one of our goals is to abstract any worries of node infrastructure away from application teams. So we want to be able to serve applications that request all different types of CPU and memory. In addition, with things like VPA, we know that the resource requests of pods might not be static, they might be dynamic, and we still want to be able to bin pack these workloads. So the question then becomes, how can we bin pack thousands of unique workloads? To solve this problem, rather than approach it from a theoretical point of view, we decided to use scheduling simulations. We built a component called the Instance Type Advisor. The goal of the Instance Type Advisor is to run scheduling simulations for the sets of pods that run on our node group sets against every possible instance type that we could use, and then rank those instance types based on which are best for bin packing efficiency. So as an input to the advisor, we have our set of pods, which we can select via a node selector. For example, get all pods running on nodes that have label foo equals bar, or concretely for us, get all pods that are running on the nodes of our node group set. The next thing we'll pass to the expander is an instance catalog, which is a catalog of all possible instance types that we could use, including their specifications like cost per hour and CPU and memory capacity. Within the advisor, we also have a virtual node builder, which is just an interface to build virtual nodes in order for us to schedule onto them that match the specs of the instance catalog. And for the actual scheduling simulations, we use the upstream Kubernetes scheduling framework, but we could use other scheduler plugins if we needed to. So the results of the instance type advisor in a single cluster might look something like this, where we have our current instance type that we're using, which is m6a.8xlarge. And we can see that with this instance type, our requested CPU percentage is down at 62%. What the advisor tells us is that if we were to reschedule all of those pods currently running on mainly M6As to R6a.4xlarge, we would increase our requested CPU percentage all the way up to 95, improving our bin packing efficiency, and therefore, we can see this translate to a significant cost decrease in our fleet. So we run scheduling simulations like this in every single cluster, and we store the results of them as a CRD that we can consume within the cluster. Beyond bin packing, as I mentioned, we also care about performance. So to get a more granular look at the performance of each instance type, we run performance benchmarks for network performance, CPU, memory, and storage. And this allows us to weigh cost versus performance for every instance type. So for example, before we make a migration from instance type A to instance type B, we could take a look at these benchmarks and make sure that they match up and we won't introduce any performance degradations. Furthermore, we can account for these in our cost calculations. So for example, if we look at CPU performance, we might see something like instance B is 20% more expensive than instance A, but in fact it's 30% more performant. So what that could mean is that if we're properly auto-scaled on CPU, then if we use instance type B, we might be able to run 30% fewer instances than instance type A, and that affects our cost calculations in the end. For reliability, we know that there's a lot of different reliability concerns that go into instance type selection. For us, we care about things like the capacity of each instance type, and as I mentioned before, we also care about the size ranges of our instance types that we use to serve a diverse set of pods, and we also might want to express performance preferences. Additionally, these reliability concerns might be different per environment that you're running in. For example, the capacity of instance type A might be different in region X than it is in region Y. And so to give us flexibility in making these reliability choices, we built a small library that allows us to build cell-go selectors against instance type attributes, as well as attributes within the environment. And so this allows us to build selectors like the following. For example, if I know that I want to use M6G, R6G, or C6G because I have a deep capacity pool, and I know I want to serve applications between 8 and 32 CPUs, I can build a selector to represent that. If I know that I have network-intensive applications in edge environments, I can build a selector to select network-intensive instance types for that environment. If I know that a specific cluster can benefit from newer generation instance types that might be more expensive, but are also more CPU performant, then I can build a selector for that as well. And even if the cloud provider releases some sort of fancy new type that I'm not sure I want to use in prod yet, but I want to test out in my experimental environment, I can build a selector for that too. So with these three tools, we now have the advisor to be able to calculate the bin packing efficiency of all of our node group sets for cost optimization. We have benchmarks to factor in the specific performance of every instance type, and we have attribute selectors on the instance type and environment to give us flexibility in the reliability concerns that we care about for our fleet. So at this point, we feel like we have a good set of tools to be able to identify optimal instance types, and so now I'm going to pass it to Rahul to figure out how we scale those optimal instance types.
All right, so now we're going to scale the best instance types. So right now, this is our auto-scaling ecosystem. We're going to build on this diagram as we go through the presentation. But for now, we have the instance analysis tools on your left that Ben just went over. And this will let us know what the best instance types are. And then on the right, we have our simple auto-scaling ecosystem with the cluster autoscaler and some node groups. So we as humans, through the instance analysis tools, know what the best instance type is. But now the question is, how does the cluster autoscaler know what the best instance type is? And this is important so we can apply the analysis. And I want everyone to remember this question, because it's going to come back later on in the presentation. So to tell the cluster autoscaler what the best instance type is, we use the gRPC expander, like Ben mentioned. It's a gRPC service where you can put whatever custom code you want in there, and it'll influence the scaling decisions of cluster autoscaler. But this kind of just pushes down the question to the gRPC expander. We actually have to write this custom code so that it can properly influence cluster autoscaler. So a simple way to influence the gRPC expander is just human operator. So the human operator can get the instance analysis results themselves and write that in a format which the gRPC expander can read, something like a config map or CRDs. So in this example, node group C has the highest score of 100. So gRPC expander will tell cluster autoscaler to scale that instance type. So we wanted to validate this whole approach that we've been taking so far of optimizing instance types. So we picked one of our clusters that we saw had the most bin packing potential based on our analysis. And in this case, we are running on M6G.8x large instance types, which have a more balanced CPU to memory ratio and are meant for general purpose workloads on AWS. But through our simulations, we found that there are more memory-intensive workloads on this cluster, and that R6G.8x large would be a better fit because it has a higher memory to CPU ratio. So you can see on the top graph, we significantly reduced the number of instances we needed. And on the bottom, you can see we significantly reduced our costs by over 60% in just this one cluster. So this validated to us that our approach of choosing the optimal instance type did in fact work, and we wanted to expand this to the dozens of clusters that we run on. So if you're running in a small shop with just 1 or 2 Kubernetes clusters, this approach works perfectly fine. With a human operator, it's not too much manual toil. You can kind of get away with it. But at our scale, we run on dozens of clusters. So the best instance type is not going to be the same across clusters. You could have one cluster that runs a bunch of memory-intensive applications, another one that runs CPU-intensive applications. So it's going to have completely different best instance types. Also, across regions, there's different instance type availability. Across cloud providers, you have completely different instance types. So a human managing the best instance types across all these clusters is not going to scale well. The other thing is that these scores can potentially change frequently. Let's say in the middle of the night, an instance type runs out of capacity. You're going to have to change the score of that instance type. Or if a new application gets deployed or scaled up, you're going to have to change the score for that too. So a human operator can't really handle all of this. We're going to have to go back and replace the human operator with something that's more scalable and dynamic so that it can optimize costs across our dozens of clusters. So what we did was we created a new custom controller called the instance scorer. This will basically automate what the human was previously doing, and that'll watch the instance analysis results and then write those to config maps, which the gRPC expander can read, and then influence the cluster autoscaler. So because of this new automation, we were able to do this migration across dozens of clusters. On the top, you can see the number of instances we migrated. On the bottom, you can see our yearly potential cost savings going down. So potential cost savings is a calculation we do where we take the current costs of our clusters and subtract the optimal cost if we are using the optimal instance type. So let's say like a cluster costed $10 million running on a non-optimal instance type. But if we were to change it to the optimal instance type, it would only cost $6 million. That means that we have a potential cost savings of $4 million. So in this case, across our dozens of clusters, we had $4 million in potential savings, and we were able to save this money automatically. So when I say automatically, you can see on the dates of the graph, it's from late July to early September, so around 1.5 months. So that's still quite a while. And although a lot of the process was automated, we still had some manual work to do. So taking a step back, this is just a list of AWS instances. There's hundreds of them, and they each have their own characteristics. And in our diagram that we have so far, if instance type A, B, C, or D happen to be the best, then we're just fine. Cluster Autoscaler will be able to scale it up. But what happens if instance type N happens to be the best? Well, it doesn't exist in our cluster, so Cluster Autoscaler can't scale it up. It has to scale up the next best available option, and you might not get the full cost savings through that. So now we come across the question, how do we make sure the best node group exists in our cluster so that we can get the max savings? So one easy approach is just create a node group for every single instance type. So you'd have hundreds of node groups on your cluster, and no matter what the best instance type is, you're guaranteed to have it, and Cluster Autoscaler can scale it. But the problem with this is it significantly impacts the Cluster Autoscaler performance. In this case, in one of our clusters, we had a few hundred node groups, and you can see on the bottom, the main loop P99 duration, sometimes it took over 5 minutes. So imagine you're in an incident and you need an urgent scale up, and you're waiting over 5 minutes to get your nodes. You're probably going to be upset. So we realized that we can't just simply create a bunch of node groups for no reason. We have to be efficient with it. So we did some cleanup, and you can see the P99 duration dramatically went down from over 5 minutes to less than 10 seconds. So as a platform, we have some requirements that we need to have for our users. And based on those requirements, we can create a node group set and see which node groups we actually need. So one requirement is we need to scale the most cost-efficient instance type, so we can have a node group for that. Another requirement is we need to schedule pods requesting up to 64 CPUs and 256 gigs of memory. And the best instance type might not necessarily be able to do that. It could only have 16 CPUs, so it can't schedule a pod requesting 64 CPUs. So we're going to need another node group that has an instance type that's big and is also cost efficient. Another thing is at our scale, we often can't rely on the cloud provider having enough capacity for a single instance type. We're going to have some fallbacks just in case. So we're going to create 2 fallback node groups for each of these main instance types. So now we have 6 node groups in our node group set, and we're going to guarantee we always have the best node group while not creating too many. So in the past, during that 1.5-month migration I was showing, a lot of it was automated because in a lot of cases, we did already have the best instance type on the cluster. But in a lot of cases, we didn't. And we'd have to manually go in and create node groups for them. So we already know that at our scale, we can't continue manually doing this. We need to automate it so it works across all of our clusters. So what we did was we created a new component called the node group set controller. This will see the node group set, see its requirements, and reconcile with the cluster what node group should actually belong. So now we come to the question, how does the node group set controller know what the best instance type is? And if you remember, I told everyone to remember a certain question before. And the old question was, how does the cluster autoscaler know what the best instance type is? And now I've just replaced the cluster autoscaler with node group set controller. It's asking the exact same question. And when we answered it for Cluster Autoscaler, the answer was the gRPC expander. So you might be wondering, what's going to tell the node group set controller what to do? And it's the gRPC expander yet again. So you might be a little surprised or curious, like, hey, I thought this gRPC expander was a Cluster Autoscaler thing. Like, how are you using it with this new component that you created? Well, that's another benefit of the gRPC expander. You can put whatever custom code you want in, sure, but it's just a gRPC service. There's nothing restricting the Cluster Autoscaler from being the only thing that can communicate with it. We even communicate with it from our own laptops when we want to sanity check that our instance type rankings make sense. So through that, any service component you make can make a gRPC request to the gRPC expander and ask it, what are the best instance types? So this closes the loop on our autoscaling ecosystem. On the left, we have our instance analysis tools. We get the results. Instance Score watches these results and writes them into config maps, which the gRPC expander reads. So now the gRPC expander knows what the best instance types are. Through that, the node group set controller can now create the best node groups on the cluster, and Cluster Autoscaler will then scale these node groups. So we saw this take action in one of our clusters. It was previously running M6G.8x large instances for quite a while. And then you can see a spike in the number of nodes. And that's because a new application got deployed to this cluster. So originally, it was running on M6G.8x large. And then our instance analysis showed us that C6G.4x large was the best. And our cluster didn't have this node group. So the node group set controller created this node group for us, and then Cluster Autoscaler started scaling it. So you can see, as we switch to the blue C6G.4x large instance types, our potential yearly cost savings went down by $2 million. So we've saved millions again. So we've accomplished both of our goals now. We're able to both identify and scale the best instance types. So next steps for our platform, we want to continue what we're doing. We want to continue abstracting these low-level infrastructure details from our application teams. Just like the example I showed, this application team didn't really have to worry about the underlying infrastructure, like what instance type they're going to get scheduled on. They could worry about their application, get it deployed, and then our cluster would automatically adapt itself to be more cost efficient. Another thing we want to expand on is providing different varieties of instance types. Like Ben mentioned, at Datadog, we have many different products, many different types of workloads that each have their own requirements. So we need to have instance types to fulfill these requirements, things like local disks, for example. And then another avenue that we want to explore is optimizing the placement of our applications. Throughout this talk, we took existing clusters and their set of applications and adapted to that. But what if preemptively we could move an application from one cluster to another or decide where a new application should go because it has better bin packing potential on one cluster over another? So these are avenues we're looking to explore to continue improving the platform we provide to our application teams. So thank you, everyone, for listening to our presentation. We have our LinkedIns on the right side of the screen in case you want to connect with us. We have the feedback form on the bottom left. And we're also on the Kubernetes Slack in case you want to message us and meet up while we're all still in London. So thank you, everyone, for attending our talk, and we'll take any questions.